In this video, I'm going to talk about the Bayes theorem. So let's get started. Before talking about the Bayes theorem proper, I'm going to dive a little bit into probabilities. So imagine you have two events. We have event A and event E. The probability of event A happening is known as the marginal probability. It's known as the marginal probability of A. The same thing goes to E. When you determine the probability of E happening without any other condition, you call that the marginal probability of E, right? But then, if you are told that what's the probability of A and E happening, you call this joint probability. So joint probability of both A and E happening at the same time. Then another term I need to introduce you to is conditional probability. If you are told that what's the probability of A happening, given that event E has happened, you call this conditional probability. Conditional probability of A. So these are some of the terms you need to familiarize yourself with. So when you have just a probability of an event, it's typically referred to as marginal probability. But if you say you want to look for the probability of both events happening at the same time, then you call that joint probability. Then if you are interested in a case where you want to get the probability of A, given that event E has happened, you call that conditional probability. So here is the issue here. How are these things connected? How are they all connected? So let's take a look at this scenario. So let's say you throw a dice, for instance, and you are told what's the probability of 4 showing up. That's just marginal probability. Just compute the probability of 4 showing up, which is just 1 over 6, right? One outcome divided by 6 possible outcomes. But then, if you are told that what if you throw the dice twice and you are asked what's the probability of one 4 showing up and the next one being 5 showing up, then you are looking at joint probability because you are looking at probability of 5 and 4 showing up. In that case, you call that joint probability. But then if you are told that you should look for the probability of an event happening, given that the first one has happened, then that's conditional probability. So an example is this. Have 4 red balls in a bowl, and you also have 6 white balls in a bowl. So here's the question. If you are asked to pick 2 balls at random from that bowl, and you are told that what's the probability of picking a white ball, given that the first selection was a white ball. So what this means is, what's the probability that the second pick will be a white ball, given that the first pick is a white ball? And this time around, there's no replacement. So that means if you pick the first ball, you are not expected to replace it. So in this kind of scenario, this is a conditional probability where you are looking for the probability of the second ball being white, given that the first ball is a white. So in that case, you know that when you pick the first ball, and if it turns out to be white, it means you'll be left with 5 white balls, and the total balls will be 9. So which means this probability will be 5 over 9. So this is the conditional probability of picking a white ball, given that the first pick is a white ball. But this is just to touch on some of the concepts we are going to be discussing under Bayes theorem. So let's go into conditional probability before we talk about Bayes theorem. Formula for computing conditional probability derives from some of the idea about joint probability. So let's look at this joint probability. The joint probability of A and E happening can be expressed in two different ways depending on certain conditions. So let's say it turns out that A event A and E are independent. So independent means those two, the first event does not affect the second event. That is, if A occurs, it has no impact on E happening, right? For this situation where you have independent events, so in the case where you're assuming that A and E are independent, this joint probability can be expressed as the probability of A times the probability of E. So this is how you express joint probability once you know that A and E are independent. But what happens if A and E are dependent? If the occurrence of A has some impact on E, or if the occurrence of E has some impact of A. In that case, the joint probability is expressed as the probability of E times the probability of A given that E has occurred. So this can also be written as the probability of A given times the probability of E given that A has occurred. So what's the difference here between when A and E are dependent? So the key difference is, if you notice, we still have one, we still have probability of E and probability of E here. But here is where we've got a difference. Once they are dependent, it means you are going to multiply by the conditional probability of A, given that E has occurred. But if you choose to start with the probability of A, then you are going to get the probability of E, given that A has occurred. So we can easily infer from here that the conditional probability of A, given that E has occurred, is simply the joint probability divided by the probability of E. Then the same thing goes to this. The conditional probability of E occurring, given that A has occurred, is the probability of E, is the joint probability of A and E divided by the probability of A. So this is the formula for computing joint probability. We are still going to talk about how this relates to Bayes theorem. So that's exactly what we're talking about next. So, but one thing you need to note is this is the conditional probability. This is the marginal probability, and this is also marginal probability, right? So let's now talk about Bayes theorem. Bayes theorem derives from the formula of conditional probability. So let's take a look at the probability of A given E as occurred. You can express it as the joint probability of A and E, right? Divided by the marginal probability of E. So the whole essence of Bayes theorem is to express this formula in a way that it can be used in practical terms in real life. Because the way it's represented here, it's quite elegant, but then in real life, the way information is available to you is not going to be in form of joint probability. And Bayes theorem is an attempt to represent this formula in such a way that it can be used in most fields. If a Bayes theorem is typically seen as a theorem for updating one's belief, and I'm going to talk about that shortly. So let's take a look at how Bayes theorem connect this whole thing. Remember that we have the joint probability of A and E to be the probability of E, the marginal probability of E times the probability of A given that E has occurred. And we also know that this is also the same thing as the probability of A times the probability of E given that A has occurred. right? So what does this mean? So this means we can express the probability of A given that E has occurred. We can express it in terms of this. So we can say, instead of having this, we can say it's equal to the probability of A given times the probability of E, given that A has occurred, divided by probability of E. So this basically is the Bayes theorem. So this is the Bayes theorem. So it's just all about replacing the numerator with this equivalent expression. So that's Bayes theorem. So the question is, what makes this new expression better than the previous? So why this is more usable or practical in real time. So in this case, the way Bayes theorem is being used in real life is as follows. This probability is typically called the posterior probability of hypothesis A. So that's what this particular part is known as. Then this part is typically referred to as the prior probability, the prior probability of A. Then we call this probability of A given probability of E given A, we refer to this as the likelihood, the likelihood. Then we already defined this to be the marginal probability. So this is marginal probability, right, of E. So this is how these terms are generally referred to in the world of Bayes theorem. But then there's one more thing I need to talk about, which is how do you compute the marginal probability of E? It's generally calculated in a very tricky way because typically you don't measure the probability of E in real life. So let me just show you how the probability of E can be calculated from other information. Recall that according to Bayes' theorem, the probability of hypothesis A given event E or evidence E is equal to the probability of A times the conditional probability of E given A as occurred divided by the probability of E. But then the probability of E is often not measured in real world directly. So how do you compute the probability of E? Typically, you will need to compute that from the other information like the probability of A given times the probability of E given A, right? Then plus the probability of the opposite or alternative event of A. So let's say there are two possible events that could happen. So let's say event A could happen and the negation of event A is event B, right? In that case, we could say that this marginal probability of E is equal to this part plus the probability of B times the probability of E given B as occurred. You can easily derive it from the conditional probability. You can easily derive it. So, but I'm not going to go into the derivation, but this is how you can represent the the marginal probability of E. We will get to understand better later. Okay, but then instead of writing this equation this way, you can represent it as the probability of A times the probability of E given A, then divided by this sum, which is the probability of A times probability of E given A plus the alternative. So let me represent the alternative event as this, then times the probability of E given that the alternative to A has occurred. Sometimes it's written as follows. Sometimes as follows. You could say probability of E given A, then divided by summation. So just add up all of this. So let's say all possible uh, events, right? So this is I, given that E given AI, then you simply say from I to whatever the value of the number of possible alternative events. So this represents the Bayes theorem. I'm going to use the following examples to illustrate this theorem and to show you how powerful or how relevant it is in many aspects of science. Let's take a look at this example. Imagine you have a particular school, and in that school you have two classes. So this is class A and this is class B. And in this particular class, you've got 30 students. In this particular class, you've got 70 students. Then let's say you got some students that love football. Now, let's represent that group of people with this shape, right? With this rectangular shape. So let's say inside this group, so this is the football lovers. So this is the football lovers, right? Football lovers. So let's use F to represent it. And here we've got 15 of them, and here we've got 20 of them. So it means in class A, 15 students, they love football. And in class B, 20 students love football. Obviously, altogether, we've got 35 football lovers. So here's a question. What's the marginal probability of A? What's the marginal probability of B? What's the marginal probability of F, right? To calculate this is straightforward. To calculate the marginal probability of A, just take 30 divided by the total number of students. So that's the population size, which happens to be 100, and that's what 3 over 10. So what about the marginal probability of B? That's 70 over 100, and that is 7 over 10. Then what about the marginal probability of football lovers, F, which will give you 35 over 100, and that will be equal to 7 divided by 20. So now, let me ask another set of questions. What's the joint probability of A and F? So what this means is, what's the probability that a student picked at random is in class A and also loves football? So joint probability. So how do you figure that out? So in this case, what the question is just telling you is what probability of this region, right? Because this is where you have the intersection with respect to the entire population. Note that with respect to the entire population, and that's 15 over 100, and that will give you 3 over 20. What about the joint probability of B and F? That is 20 over, that's this region, 20 over 100, and that will give you 1 over 5. So next, what about the probability of A given that the person loves football? So what this means is, if you pick a student and you know, and the student has revealed that he or she is a lover of football. So the question is, what's the probability that that student belongs to class A? So what's the probability that a given student that has declared he loves football or she loves football, what is the probability that that student is in class A, right? So this is conditional probability because this question is saying what probability that you are in class A given you love football. So how do you think about that ratio? What ratio are you going to look into? Okay, so first is you are going to take the way this conditional probability works is once you look at the evidence, which is F. F is typically the evidence, right? So the person has declared or has shown evidently that they will love football, right? Which means you are interested in this zone where you have 35 students. So the question is, what's the chance that the person belongs to class A, which is 15, given that the person loves football? So all you will do is you take 15 over 35, not over 100. When you take it over 100, you are looking at joint probabilities. But when you say what's that 15 as a ratio of those playing football, then you are talking about conditional probability. So here you have 3 over 5. So what about we figuring this out using the formula? Okay, yes, you can do that. You'll see you get the same result. So let's say we decide to use the formula. You're going to get something like the probability of A uh, and F, right? Divided by the probability of F. And that will be what's the joint probability here? That's 3 over 20. Then what about the probability of, note that this is 3 over 7, not 3 over 5, because if you divide by 5, you get this. So here you have 3 over 20 divided by 7 over 20. And at the end of the day, you're going to get 3 over 7. So it gives you this, right? So what about this other question? What's the probability of B given F, given that the person loves football? We take this region, which is 20, divided by the total number of people that love football, which is 35. And you can prove this by using the formula, which is the the probability of B given F is equal to the probability of B and F occurring at the same time, divided by probability of F. And that will be 1 over 5 divided by 7 over 20. And that will give 20 over 35. So this is what Bayes theorem is all about. It's all about you taking the the subset within your evidence group and dividing it by the total number of people in that evidence group. So that's what Bayes theorem is all about. But then the way you compute Bayes theorem is different from the way you compute the usual conditional probability problem, where you just take the joint probability divided by the marginal probability. In most cases, you won't get your marginal probability direct. So we're going to go into that in the examples that follow. There's something to mention here, which is when you want to apply Bayes theorem in general, like in this particular scenario, it is assumed that the alternative to event A must be, which is event B, must be mutually exclusive. So what that means is the joint probability of A and B must be zero. In other words, the two events should not intersect. And what that also means is the probability of A plus the probability of B must be equal to 1. So that's one condition you need to note. When computing things within the realm of Bayes theorem, the sum of the marginal probabilities of all the alternative events must be equal to 1. So now let's take a look at more examples. So let's take a look at this example. So here you've got an oil company owning or purchasing a land that has prospect of having oil. And there are three possible events that could happen here. So this is how you document these problems. So the first one you do is to itemize the events. So the events include the following. So you have A1. So A1 is the event of finding high quality oil. Then A2 is the event of finding a premium quality oil. Then A3 is the third possible event of finding no oil. All of them, they are mutually exclusive. If you add up all the marginal probability of each of them, you get you get one. So this is the probability of the A's, right? So if you of AI. So if you look at this, you will see that the probability of A1 is 0.50, 0.20, and 0.30. Everything should sum up to 1. So the next is, let's continue with the question. So the question is, what's the probability of finding oil? So what's the probability of finding oil in general, right? So, well, the way to think about it is, what are the events that are categorized as finding oil? And that you can figure that out as follows. So it's the same thing as the probability of finding either medium or either high quality or medium oil. So it's just for you to sum up these two probabilities, which is 0.7. So 0.7 is the probability of finding any type of oil in general, right? So, but note that this is the marginal probability of finding oil. So one thing that may come to your mind is, how do companies come across these marginal probabilities? Well, it's easy. So let's say, for example, you have got a company, maybe the company has drilled 100 wells. So let's start of the 100 wells, they've found, let's say, 20 high quality oil, and let's say they found 50 medium quality oil, and maybe 30 cases, no oil at all. This finding is known as just the marginal probability, just the probability of what they figured out over the years, right? So that's marginal probability. So it's just like an historical uh, information about their experience. But then they want to know the chance of finding oil for this particular well that they figured out. So one thing you should know about drilling is the way engineers go about it is, once they start the drilling, they take tests along the line to see if there's any prospect. And once the probability of finding oil goes up as they get more tests done, they continue drilling. Once the probability keeps going down, then they stop drilling. They don't necessarily get to finish the entire process before they stop the drilling. So in this particular case, after 200 feet of drilling on the first well, they performed a soil test, and the soil test gave the following result. So you can see the probabilities of the soil test as evidence. So we call that the evidence, right? So as you keep drilling, you want to gather more evidence to know whether you should stop the drilling or whether there's hope at all. Note that at this point, they have gotten the soil test and that particular soil has been identified. But here is what they know from history. From history, they know that the probability of finding that particular soil, given that this oil was found, that is, this particular oil or event occurred, is as follows. So this is the condition, this is the likelihood. So I'm going to throw more light on the 0.2, 0.8, and 0.2. So what this information is saying is, what's the whenever high quality oil is found, whenever they found high quality oil, how many times do they come across this particular soil that has been detected? So which means the chance, the percentage is 0.2, right? What that means is 20% of the time that they find high quality oil, 20% of the time, this soil is detected whenever they find high quality oil. Now, this other information means whenever they find medium quality oil, 8% of the time, this soil is encountered. This soil is just confirmed, is encountered. Then this third property means whenever this low quality and this scenario of no oil being found, no oil at all, they encounter this soil just 20% of the time. So one way you can visualize this is you can visualize this graphically where you have three possible events: A1, A2, and A3, right? Then you have this evidence which cut across these three events. So this section is 0.2. That's the probability, the conditional probability of finding this soil type, given that you actually detected a high quality oil, whereas this is 0.8 and this is 0.2. So that is how you think about it. So this S is an evidence, but then you need probabilities based on history of finding that evidence, given that those events must have occurred. So that is what this represents. So the first thing is the question is saying to interpret the soil test, which is what I've just done, the meaning of or the implication of this soil test. What it means is it is an evidence that will help us update our belief about our chance of finding uh, high quality or medium quality or no oil at all. So the next question is we should update our prior knowledge. So this is our prior knowledge. All this marginal probability of event one, two, three, right? They are prior knowledge, just historical knowledge about our chance of finding those, getting those events. So, but now we've got an evidence. So, what's now the new, which is known as the posterior probability? What's that? So, that one is typically represented as the probability of A given S. So, now what's the probability of all the A's given evidence S, given that we found a particular soil type? What is that probability? So, this is how we go about calculating it. The revised probability, which is known as the posterior probability of A given S, is the probability of the prior probability times the probability of S given A divided by the probability of the marginal probability of S. So this is the formula which is obviously the Bayes theorem that we're going to apply. So what we need to figure out now is we need to know the probability of S, and we also need to compute this product. So let's do that using this table. So here's the redrawn table. So the first one you do is to take the product of the prior probability and the likelihood. This is known as the likelihood. If you take that product, this will give you 0.1, 0.16, and 0.06. Then the next one you do is to compute the condition is to compute the marginal probability of the evidence, which is basically the sum of this. So the sum of all this will give you the probability of the the marginal probability of the evidence. So if you add this up, you're going to get 0.32. So now we can now compute the revised or posterior probability by just dividing this part, which is the numerator, by the marginal probability. So 0.1 divided by 0.32, that will give you, to give you 0.3125. Then this will be 0.16 divided by 0.32, and that will give you 0.5. Then the third will be 0.06 divided by 0.32, and that will give 0.1875. This is what you need to know. The sum of all the revised or posterior probabilities must also be equal to 1. But the sum of the likelihood doesn't have to be equal to 1. Likelihood colon and unnecessary, they are not mutually exclusive. So you shouldn't expect them to be 1. It's not a must they are equal to 1. But the the prior must be 1 and the posterior must be 1 as well. So this is how you update your belief about a field. So the summary of this problem is you start off with an assumption, which is like an historical knowledge about the world, about the company. So the company typically has figured out that 50% of the time they drill high quality oil, 20% of the time they drill medium quality oil, and 30% of the time they find no oil in all their drilling exercise. But for this particular well, they tested the soil at 200 feet. And then that soil is the soil they figured out is known as soil S, right? They found out that it's a soil S at that depth. Then they went back to their archive and they realized that 20% of the time that they they drill high quality oil, soil S is found. 80% of the time that they drill medium quality oil, soil S is found, and 20% of the time that they find no oil, soil S is found. So this is what is known as the likelihood, and it's also the likelihood is the probability of the evidence given the event, right? So that is the likelihood. So the next thing is once you've gotten your likelihood and you know your prior, you can compute the rest. So you can use that information to you get the product of the prior and the likelihood, and that gives you the fourth column. Then you add up the fourth column to get the marginal probability of the evidence. Then you use this as denominator. Then you divide each of these by this denominator, and that gives you the posterior. Now, what's the decision here? The decision here is there's a high chance of finding there's a higher chance of finding a medium quality oil. Based on this new evidence, we can say that they have a higher chance of finding medium quality oil compared to every other event. So that's just what Bayes theorem is capable of doing. It's capable of informing or updating belief about something. So there's a prior belief. From the prior belief, we are expected to have high quality oil. High quality oil has 50% likelihood. But with the new evidence, it turns out that medium quality oil is more probable. And you can add more evidence to this. You can, let's say there's another test. You can keep adding more evidence and keep updating those beliefs until you get to a point where you make your decision. So this is a very interesting way. Uh, this is a very interesting way that Bayes' theorem is used in real life to update a prior knowledge or prior belief about events. So let's take a look at another example. Let's take a look at this second example. This example is all about the application of Bayes' theorem in the medical field. So let's solve it this way. So here we've got our table. So the first thing we want to define is you want to define the events or the diseases. We have D1 and D2. The second thing you want to define is our prior knowledge, our prior probability about the occurrence of those diseases. So, which is the probability of D occurring. So, for the first one, the probability is given as 0.6. Then, for the second disease, the probability is given as 0.4. And if you check this out, they sum up to 1. They must be mutually exclusive. They must be mutually exclusive. So, the next thing I want to do is, okay, if you read the question properly, you realize that you've got a patient and this patient could have one of these two diseases, right? And and the situation here is the hospital or the medical center has carried out some tests and they've got three possible symptoms that could occur, right? So you have symptom one, symptom two, and symptom three. Then we were given the probabilities of the conditional probability of those symptoms given the disease. So the way you think about it is as follows. What is the probability of a given of S1 given any disease? So what this means is historically, whenever a particular disease is reported, what's the chance that that symptom will occur? So for the case of the first disease, the chance that you will notice that symptom is 0.15. Then for the second disease, the chance that a patient will experience symptom 2 is 0.80. So you can see this information as historical information. Maybe the hospital must have or research must have proven that whenever you have this disease, you have this given chance of experiencing that symptom, right? So that's what this likelihood data is all about. But this is just for the first symptom. So for the second symptom, which is S2, so what's the conditional probability of you um, observing symptom 2, given you know a particular disease has taken place? So for this one, it is 0.10 and 0.15. Then for the third symptom, you have S3, the probability of S3 given the disease has taken place, and that is 0.15 and 0.03. So here's the question. So the question is that we should use this information to compute the posterior probabilities of each of the disease given the following, given that the patient has symptom 1. The second question is given that the patient has symptom 2. And the third question is given that the patient has symptom 3. So this is what it means. It means what should be your new belief or your new probability for each of the diseases, given that this patient has just symptom 1, right? So that's what question 2A is all about. Then question 2B is saying, what would be your new belief, your new probability for each disease if you know that this patient has symptom 2? So what this means is for question A, you are interested in probability of the D given S1. So when I use D, I'm referring to both D1 and D2. So then B is the probability of any of the disease given symptom 2, and C is probability of any of the disease given symptom 3. So these are the questions. We'll talk about question 4 later, but these are the questions they want to answer for A, B, and C. So to calculate the first one, you just focus on this first likelihood. So what you need to compute here is you need to compute the product of the prior probability and the likelihood for symptom 1. And here's how you go about it. So let's continue the table here. So let's say this is the probability of the disease times the likelihood for symptom 1. So in this case, you just take the product 0.6 times 0.15, and that will give 0.09. Then for the second disease, that's 0.4 times 0.8, and that will give 0.32. So the next thing we want to do is to add this up. If you add it up, you are going to get the marginal probability for the symptom 1, and that will be equal to 0.41. So the next thing we want to do is to compute the probability of the D given symptom 1. So that will be equal to you taking 0.09 divided by 0.41, then 0.32 divided by 0.41. And this will give you 0.22 and 0.78. So this answers the first question, which is the new belief about the the chance of the patient experiencing a given disease. So what this tells us in summary is there's a higher chance that this patient is suffering from disease one, given the first evidence, given the first symptom, right? So that's what this information is telling us. So let's now look at the second case. What if we detected the second symptom? How would the trial probability change? What would be our new belief about the most likely disease that patient is going through? So let's take a look at the second question, which is what would be our new belief, our posterior probability, if it turns out that the patient is showing signs of the second symptom. So the first one we do is to take the product of our prior belief, right, times the likelihood for symptom 2. So if you take that product, means you say 0.6 times 0.1, that will give you 0.06. Then 0.4 times 0.15, that will give you 0.06. Then if you add this up, you will get 0.12. So the next one you do is to take this and divide by 0.12, and that will give you 0.5, and this will be 0.5 as well. So what this indicates basically is if this is the prior probability, which is the probability of the given S2 symptom is being reflected. So this indicates that if the patient is reflecting symptom 2, there's a 50-50 chance that it will be disease 1 or disease 2. Basically, that's what this means. So this symptom does not really give us any strong indication whether it is disease 1 or disease 2. For the third question, we are dealing with symptom 3. So the first one we do is compute the prior probability, the product of the prior times the likelihood for symptom 3. So in this case, we're going to multiply this 0.6 times 0.15, and that will give 0.09, and this is 0.012. So let's take the sum of this. That will give us 0.102. So let's compute the updated or the revised probability, which is probability of disease given S3, given symptom 3 as well. So we take 0.09 divided by 0.1. So this is basically the marginal probability of the third symptom. So let's compute this. This becomes 0.88 and this becomes 0.12. So what this shows clearly is that if symptom 3 is expressed, there's a much more likelihood that the patient is suffering from disease 1. So let's move on to the fourth question. So the fourth question is a bit interesting. So it says, for the patient with symptom S1 in part A, suppose that symptom S2 is also present. What are the revised probabilities of D1 and D2? So this one is stating that imagine we have detected symptom 1 and we now confirm again that symptom 2 is present. What will be the revised probabilities? So the first thing we do is to look at how to express this. Then now look at how to compute it. So let's take a look. Specifically, the way you treat this kind of question, that's question 2D, is you treat it as follows. You treat it as though you are looking for the probability of the given S1 and S2 have occurred. So in this case, you've got two evidence. So you are looking for the probability of D given two evidence. So the way you express it is as though you are looking for the probability of D given S1 times the probability of S2 given D, then divided by the probability of S2. So this is how you should think about it. So your trial becomes this part that you've calculated before. And if you can recall, this probability of D given S is the probability of D given S1 is as follows for both D1 and D2. So it's 0.22 and 0.78. So we're going to use this information to compute the this probability of D given two evidence. So this is how you go about it. So this becomes your trial, because the way Bayes theorem works is you can update your evidence with new evidence, and you don't necessarily need to have just one evidence. Even if you have more evidence, you just keep taking your last computation as your trial, then then use that to calculate your new posterior and keep going on that way. So in this case, we now need to we already know that the probability of S2 given D is 0.1 and 0.15. So we can use this information to compute the product. So we can just say the probability of D given S1 times the probability of S2 given D, right? So this product, so that will give you 0.022, and this will give you 0.117. So now that we've gotten this, so the probability of D given both evidence 1 and 2 will therefore be as follows. So you need to get this sum. The sum here will be 0.139. So if you take the ratio of 0.02 to divide by 0.139, you will get 0.158, and this will be 0.842. So this is now the new um, probability, or the revised probability, given that symptom 1 and symptom 2 have been detected. So this is a very interesting way you can apply Bayes theorem in medical field. Let's look at this third example. In this example, we have the following events. So let's list the events. We have events A1, A2, and A3. Then we have the prior probabilities of this event, and they're as follows: 0.20, 0.50, and 0.30. Then we have the conditional probabilities, or the likelihood of evidence B or event B given the event or the hypothesis. So in this case, they are as follows: 0.50, 0.40, and 0.30. So the question is, we should compute the joint probability of B given A1, B given A2, and so on. So the way you should think about it, the probability of B, not given rather, the probability of B and A1, probability of B and A2, so it's the joint probability of B and A. So the way you should think about it is, it's similar to the product. If you recall, the conditional probability of A given B is can be written as follows: A and B give divided by probability of B. This is also equivalent to B and A occurring, joint probability of B and A occurring, and divided by B. So this is one way to represent that. And of course, you can represent it in terms of the likelihood, which is in terms of the probability of A times the probability of B given A and divided by probability of A, probability of B. So this is another way to represent it. So this particular value is simply the product of this. So you just multiply this out and that will give you 0.1. Then if you multiply this, you get 0.2. Multiply these two values, you get 0.09. So when you take the sum, this will give you 0.39. So the next question, so for the first question, the answer as follows: 0.1, 0.2, and 0.09. Then for the second question, use the tabular approach to applying Bayes' theorem to compute the probability of A1 given B and it. So basically, you are looking for the posterior posterior of A given evidence B, right? So we know that to be as simple as just taking this joint probability divided by the sum. So that's 0.1 divided by 0.39, and that will give you 0.26. Then for this one, 0.51. And for the third one, that's for A3, the updated probability will be 0.09 divided by 0.39, and that will give you 0.23. And if you check this, you see that the sum is 1. Okay, so that answers the second question. So this is how you apply Bayes' theorem in updating prior beliefs or prior probabilities about events.